Question 10. The photocell shown below consists of a metal plate P and a small electrode E placed inside an evacuated class tube called a photocell. When the photocell is in the dark, the ammeter reads 0, but when monochromatic red light with the frequency off, so this is the frequency of the red light, which is 4.65 times 10 to the exponent of 14 Hertz. From a 50-watt bulb is shown on the photocell. A small current is registered on the ammeter. The table below shows the work function of two metals, cesium and gold. 10.1. Determine by calculation which metal, cesium or gold, should be chosen to make P to ensure that the photocell works with the red light. Explain your choice. Okay, so I want us to go back to this formula right here. EK. So, first of all, the work function is defined as the minimum energy that is required in order to move an electron, right? So, in other words, the energy that is provided by the light that we are using must be greater than the work function in order for us to move electrons. So let's just say if the energy that we have, the energy that is supplied by the light is 5, and then maybe the work function is 3. So our EK is going to be 2 joules, right? Now imagine for a different situation in which the energy that is provided by the light is a 3, and then the work function is a 4. So our EK is going to be negative. And then you know that you can't have negative energy. Okay. So in other words, the energy that is supplied by the light must always be greater than the work function in order for us to see the phenomenon of the photoelectric effect. Okay. So we know that E is given by HF, and then we know that W is given by HFO, right? So we can cancel the H on both sides. So it means that if the frequency of light is greater than the threshold frequency of the metal, then we will be able to experience the photoelectric effect. But if we find that the threshold frequency of the metal is greater than the frequency of the light that is provided, then there's no photoelectric effect. I hope that makes sense. So now let's try and answer the question. So we will use cesium, and then on the side we will use gold. So we know that the work function should be equal to HFO. We are given the work function as 3.00 times 10 to the exponent of negative 19. This is 6.63 times 10 negative 34 FO. So the threshold frequency for the cesium should be so I am getting 4.52 times 10 to the exponent of 14 Hertz. And then for this side, this should be 7.81 times 10 negative 19, 6.63 times 10 negative 34 FO. So the threshold frequency for the gold is, so I'm getting 1.18 times 10 to the exponent of 15 hertz. Now, you remember what we said? We said the frequency of light should be greater than the threshold frequency of the metal in order for us to experience what? The photoelectric effect. The frequency of light that we are given there for the red light, it has an exponent of 14, but that of gold is 15. So here, the frequency of the light of the red light is less than the threshold frequency of gold. So there's no photoelectric effect. Now let's check the other one. Here, 4.65 is what is the energy of the red light. And that energy, is the frequency, not the energy, the frequency of the red light. And that frequency is greater than the threshold frequency of what? Of the cesium. Therefore, we will have what? We will say, maybe let's put it in a more elegant way. Let's just say the threshold frequency of cesium is less than the frequency of red light. Thus, the photoelectric effect will happen. And then we are done. Moving on, the 50 watts bulb is replaced with another bulb with a higher intensity. So when you increase the intensity of the light, the energy of the light remains the same. Because remember, energy is given by HF. So if you are using the same light source, it means that the frequency of the light doesn't change. Since H is a constant as well, it means the energy won't change. So if you are still using the same light source, but you are only increasing the intensity, that does not affect the energy, and it also doesn't affect the EK max. A higher intensity only increases the number of photons that are released by the light per second or per unit of time. That's all it does. What effect will this have on the ammeter reading? So the ammeter reading will increase. So an increase in intensity increases the number of photoelectrons ejected per unit of time. Okay. 10.3. They say light of frequency 1.21 times 10 to the exponent of 15 hertz now falls onto P and P is made of cesium. Calculate the speed of the electron that is emitted. So here we are given the frequency as 1.21 times 10 to the exponent of 15 hertz, and then 10.3.1. They want us to calculate the speed of the electron. So E is equals to the work function plus EK max. We know that E is given by H multiplied by the frequency. This I'm not going to change because we are given the work function right there. Plus half the mass of the electron, V squared. So H is 6.63 times 10 negative 34, and the frequency is given as 1.21 times 10 to the exponent of 15. The work function is 3.00 times 10 negative 19 plus half. The mass of electron is 9.11 times 10 negative 31 V squared. So I'm getting 5.022223. V squared, and I'm just gonna divide both sides by 4.555 times 10 negative 31. So V squared should be equals to 1.1025 times 10 to the exponent of 12. Then I'm just gonna square both sides. I'm gonna find the square root of both sides. So I'm getting 1.05 times 10 to the exponent of 6 meters per second. 10.3.2. Does the work function of cesium increase, decrease, or remain the same when the different frequencies of light are used? So remember, each metal has its own work function, and the work function is independent of on the light that is used. So it doesn't matter which light you use, the work function of a metal will not change. So even if you use like a different light, that doesn't matter. The work function will always remain the same because it is characteristic to that metal. So this remains the same.